Okay, so as people come in and start rolling in, we're going to get started, everybody. Welcome to today's lecture, everyone. In today's lecture, we're going to be talking about mastering materials in game development. It's going to be, in this session, I think we're going to be doing more of a theoretical session. I won't open like engine and we won't build any scenes like that. I'm going to save that for next time, where we actually build something together. And workshop something together to learn more about materials and lighting and optimization, those kind of things. But instead, I want to give you guys a clear mental framework for how materials work in modern game engines. Because a lot of the times, material workflows are very unique to the game engine and to the way a certain person learns about it working in materials, depending on even the DCC that you work with outside of the game engine as well. And understanding how materials work is, at the core, very important as well. It's what you do as a technical artist, it's what you do as a game designer and a developer, understanding the look of the environment and optimization in the end. So we're looking at how surfaces interact with light and what PBR actually means, and how different maps like base color, roughness, metallic, and normal all work together. Now, like I said, this is today's lecture is going to be mostly talking head, just me kind of discussing and showing you all just slides as well. So the goal is that by the end, you'll understand not just what the controls are, really, but why they exist and why they're important for visual quality, performance, and collaboration in a game team as well. So, all right, let's continue. So, why do materials matter, right? A lot of the times we just kind of bash things together, and sometimes when we try to bash it, we don't really understand how things work when we first want to work on something like materials. We kind of experiment. At least like when I first started in game dev and working in CG animation, it was always experimenting with the look of a material. And so we always think about, so let's start with the why. So why spend the time learning materials instead of just using whatever the engine ships with, right? And first, materials kind of define the feel of your world. So you can have a perfectly modeled mesh, but if the wood looks like plastic, metal looks like rubber, and glass behaves strangely, the game instantly feels cheap or unfinished. Second, good materials are predictable. With a PBR workflow, once a material is kind of set up correctly, it reacts believably to different lighting conditions, day, night, interior, exterior, and without constant tweaking. Like, especially when you're new, you try to understand when you're working with materials like in Blender, and you light a scene in Blender, and then you take it into engine, any engine, let's say, you're like, why does it look different? Why is it acting different versus, you start troubleshooting those kind of things, right? So third, uh, materials have a huge impact on performance and memory as well. So when you are using high, like 4K materials, so you want to make sure things are optimized for the player also. Textures take VRAM, and shader complexity affects GPU time as well. And misusing materials can quietly destroy the frame rate, which, funny enough, even in animation, when it was not a game, it could do that as well. It can make the scene very, very heavy. And you develop the look of the game through the materials as well. And then finally, materials are shared language. When you talk about like roughness, metallic, and shader complexity and overdraw, you can have a real concrete conversation with artists, tech artists, and programmers. So this is just so basically, materials is not just an artistic topic, but it's a core production topic. So I want you to kind of think about that when you work on your games and decide what kind of textures or materials you're going to be setting up. How are the material instances, for instance, in it, no pun intended, in Unreal Engine, um, are going to work as well? How artist friendly are the controls for them to be setting up? So think about these kind of things. So what I kind of want you to take away from it in the next hour is here's like I, I want to talk about is precise idea of what a material is in a game engine beyond just the image on a mesh. A clear understanding of the main PBR channels like base, color, metallic, roughness, normal maps, ambient occlusion, and method, and what each contributes visually. So, and also you'll have a mental picture of how a material fits into the rendering pipeline from mesh to final pixel as well. And awareness of the core material workflows used in real projects, so tiling materials, trim like sharing, layering, and decals also. So, and also you'll have an understanding of how materials influence performance and memory so you don't accidentally create something beautiful but unshippable as well. And finally, a method for analyzing materials when you play games or look at screenshots. So every game you play becomes a lesson in materials. So one of the things as an artist, especially when I was in school and learning art and learning how textures work, how studying and doing real art helped me really understand textures and materials as an artist. And then when I understood them physically, I would go in with my camera outside, take pictures to see how they are made, like take a picture of a tree, and see how that texture looks like. Try to recreate it by hand, and physically, like making your own materials is very fun, and I would highly recommend that. And we'll talk about that later uh, as well. So we'll begin by separating three things that people often mix together, right? Mesh. A mesh is the geometry, vertices, edge faces. It defines the shape, and I'm assuming that we all know that. And material is a small program plus parameters that define how the light interacts with the surface. Textures are data that the material reads, so usually images storing per pixel information like color or roughness. The crucial point is that the same mesh can look completely different with different materials. So a simple sphere can be gold, rubber, glass, or mud purely based on the material and textures. And when we talk about mastering materials, we're really talking about mastering how surfaces and light behave, independent of the mesh as well. So most modern games use, of course, physically based rendering or PBR. PBR simply means we try to approximate how the light behaves in the real world instead of inventing arbitrary shading tricks per material. So for the key ideas for this that I kind of want to talk about are the energy conversion. The surfaces shouldn't reflect more light than they receive. This keeps materials from looking unnaturally bright or glowing under normal lighting. And consistency is if a material is set up correctly, it looks believable across a wide range of lighting, as sunlight, indoor lamps, night, etc. And also, let's talk about the shared language that I mentioned as well. The PBR defines standard channels and expectations, so texturing tools and engines can agree on what roughness or metallic means. The benefit for you is that learning PBR once carries between engines and tools as well. So materials and textures are kind of like a science in themselves as well. Like really thinking about how you build them from the ground up makes a big impact on the game you are developing. So across most engines and texturing tools, you'll see a very similar set of material inputs, right? We'll see the base color or albedo, as you can see here, metallic, roughness, normal map, ambient occlusion, and emissive. How many of you all are familiar with all of these? Let me know in chat. So different tools may add extra maps, but these are the core. Understanding these 6 channels already give you a strong foundation for building believable materials. So first is, base color, right? And we're going to dive into more here now in a minute, or also called albedo. The base color represents the instant color, the intrinsic color of a surface without any shading. So no shadows, no highlights, no reflections. And importantly, the base color should not include painted in shading, fake highlights, or strong baked reflections. So you can get really technical when you're setting these kind of things up. In a PBR workflow, lighting and shading are handled by the renderer, not painted manually into the base color. And also, we usually avoid pure black and pure white in the base color. Real world materials almost never hit those extremes. And keeping the base color within a realistic middle range helps the PBR model produce natural results. So when you think base color, think what color is the material under? Flat and neutral light. So understanding the real world around you also is very important for this kind of workflow as well. So going out, taking pictures of materials and textures on any kind of surface is what we kind of do. And I'm going to keep repeating that. So next, we're going to talk about is the metallic channel. The metallic describes whether a surface behaves like a metal or a non-metal. And this comes with experience also. So like when you're building the material in the DCC, you'll start to understand it and your eye develops as well. So in practice, usually 0 is non-metal, wood, plastic, fabric, stone, skin, or concrete. 1 is usually metal, steel, copper, gold, aluminum, etc. And I built so many textures and materials and shaders throughout my career that it's more of a second nature to me. So I understand how things kind of work and should look as well when you're working with real world values. And intermediate values can exist for muddy or mixed surfaces also. But for a clean material, it's usually either 0 or 1. Why this is important is because metals and nonmetals reflect light in fundamentally different ways. And nonmetals have a color diffuse response, plus a fairly small neutral specular highlight. Metals get most of the visible color from reflections. They don't have the same diffuse component. And if you set metallic incorrectly, for example, metal with metallic equaling 0, the surface behaves like plastic, not metal. And this is one of the quickest ways to break realism. So now let's look at roughness and try to understand roughness a bit more. Roughness controls how sharp or blurry reflection highlights are. Roughness 0 is a perfectly polished mirror. Roughness 1 is a very diffuse matte surface that scatters the light heavily. So again, in this class, in this lecture, we're going to be just mostly theoretical. In part 2 later, when I do this in part 2 next time, we're going to show it more in a DCC and an engine as well. So this is one of your most powerful artistic levers. Low roughness makes surfaces feel polished, wet, icy, or metallic. High roughness makes them feel chalky, dusty, cloth-like, or aged. And two materials can have the same base color but different roughness values, and they will feel like completely different physical materials. Next is normal maps. Normal maps, I feel like sometimes people have a hard time understanding how they work. I always have to explain it to like junior artists when working in a studio, as well when they build shaders and textures, and to make sure that they're building them correctly also. A normal map stores surface directions per pixel, right? So instead of changing the geometry, you know, it's telling the lighting calculation to pretend the surface is angled differently at each point. Uh, why does this matter? You're probably asking, right? It lets us represent lots of small scale detail like scratches, grooves, bumps without adding polygons. It's the backbone of high poly, low poly workflows. So most of you are trying to decide whether when you're working on a game, whether you want to work on a high poly or low poly sort of look. This is what you kind of think about. So your sculptor model a detailed version, then bake its details into a normal map on a simpler mesh. Without a normal map, surfaces lit from the side often look flat and uninteresting, right? And even a simple mesh can light and shade as if it had complex geometry. And this is one of my favorite ones that I work with is ambient inclusion as well. I can get very low level with materials and how I worked with them as well. An ambient inclusion, or AO, adds soft darkening where light is naturally blocked. So like in crevices and cracks where objects touch surfaces in tight corners. So when ambient inclusion, or AO, so if you hear the word AO in a studio and our artist is talking about it as ambient inclusion, it adds a sense of depth to the material. It helps objects feel anchored to the world instead of floating. The important part is subtly. Oh, like overdoing AO makes everything look filthy or outdated. And you want just like enough darkening to suggest physical contact and depth, not big black outlines. So that's how you want to think about AO. So in many pipelines, like the way I work with AO is stored together with other grayscale maps in one texture to save uh, memory. Another fun one is emissive. So, emissive defines how much a surface appears to emit light. Think of it on neon signs, screens, and holograms. Magic runes or power cores, indicator LEDs, and UI elements. Like a fun way to think about how so far what we've talked about is when you go outside or look at things and how light and textures are set up in in the real world, take a picture of it and try to recreate it yourself and figure out how is it set up and how detailed can you make something. So getting back to emissive combined with post-processing, for example, like Bloom, can create strong glowing effects and focal points. It's critical to remember that in many real-time engines, emissive does not automatically light other geometry. It makes the material itself bright, and post-processing can exaggerate that. But physical lighting um, is still handled by the actual light sources. So emissive for visual emphasis and mood is like not a full replacement for light. Okay, so let's zoom out and see where materials fit in the rendering pipeline for now. We've learned a lot so far already. Hopefully, uh, you guys are taking notes. And if you have any questions, you can ask them in the chat, and I will answer them later as well after the course is done. Kirsten. Conceptually, the process is that the engine draws from mesh, right? The geometry. For each visible pixel on that mesh, it evaluates the material, sampling textures, applying math, using base color, metallic roughness, and etc. It combines that with the scene lighting, direct light, environment light, reflections, and shadows. The result is that the final picture color you see is great, of course. A material is essentially a small GPU program that runs for every pixel, and the more complex the program is, more textures read more math. The more expensive it is to render. That's why material design has both an artistic and a technical side to it. And so to use textures, we need UV coordinates. Now, UVs are fun. When I first started out in CG, I didn't understand UVs. It took me a long time to understand why we have to do it this way. But then through practice, it just became more natural understanding how to do UV unwrapping as well. Um, UVs are 2D coordinates stored on each vertex that map points on the mesh to points on the texture. So good UVs mean even pixel density, minimal stretching, and themes placed where they're less visible. Now, I love the fact that we have tools that kind of help us a lot with these for like auto UVing and auto unwrapping. So I remember just like back in the day when it took hours just to UV complex unwrap. So, and bad UVs cause stretching, warped, normal maps, mismatched edges, and obvious seams. So you can clearly see it when it's not done properly as well. So PBR can't fix bad UVs. Even the best textures will look wrong if the UVs aren't poorly laid. If the UVs are poorly laid out, basically. So when you talk about good materials, it's always in combination with sensible UV mapping as well. And UV mapping is an art on its own. So most materials in games rely on tiling textures. right? And with low tiling, you stretch one texture over a large area. It looks blurry and low detailed. And with high tiling, you can get more detail, but the same patterns repeat and become obvious. Players can spot the same stain or crack over and over. So you want to make them varied and random in your game. Tiling is essential for covering large surfaces like floors and terrain efficiently, but like repetitive patterns kill the realism basically. To deal with this, teams combine tiling with other techniques, mixing multiple textures, adding decals, or layering materials so that repetition is less obvious. So there is that. So I'm kind of curious for all of you all that are working on your games. Are you building your own textures? Are you using Quicksilver Megascan? What is your process? Just let me know in chat. And in a production project, you don't want 100 completely different materials that all reinvent the wheel. Instead, you build a small set of base materials. Each describes a type of surface: painted, metal, rough, concrete, glass, and more. Many instances of those bases where only parameter values change: color, tint, roughness, detail intensity, and so on. So this approach, right, where it improves performance because the same shader code is reused, increases consistency because similar materials behave similarly under light, speeds up iteration because artists can make variations by adjusting sliders rather than editing complex graphs. Thinking in terms of reusable base materials plus instances is a big part of working like a professional team. So now let's talk about how materials are used in practice, right? There are a few classic workflows you'll see in almost every 3D game that there is. Tiling materials that cover large surfaces, like we talked about. Trim styles or shared sheets where multiple assets share one texture. Layered or blended materials where multiple materials are combined on a single mesh. Decals, which project the details on top of other materials. So each of these is a response to the same problem. How do we make big, detailed worlds without thousands of unique, expensive textures? Every team in existence always thinks about that. Tiling materials are used anywhere you have large, repeating surfaces, floors, walls, terrains, and cliffs. Um, you can cover large areas with a single texture set, but you can also get you get great reuse. The same tiling, concrete or brick, can appear in many scenes, and but for the disadvantages is that it's repetitions. Humans are very good at spotting repeated patterns. In practice, um, teams treat tiling materials as a base layer, then use other techniques like decals and layering to break up obvious repetition, especially near points of interest. So a trim sheet or shared texture sheet is a single texture that contains multiple strips or panels with different details: edges, borders, bolts, grooves, and so on. Artists unwrap many different meshes, right? Like I talked about earlier for UV, beams, rails, wall segments, pipes onto those strips. The same texture sheet can also support the same texture sheet then supports a whole kit of assets also. So the benefits of doing this are that you can drastically reduce the number of unique textures. Everything that uses that sheet shares a consistent visual style. It's very memory friendly because many meshes all point to one texture. This is especially popular like in sci-fi and architectural environments where you can reuse surface motifs a lot. Cool. So two more important ideas are layered materials and decals, which we should understand when we're working on games. Layered materials. Let's talk about that. You blend multiple materials together on one mesh. The blending is controlled by masks or vertex color. Typical use cases are blending grass into dirt, dirt into rock, wet patches into dry ground, or adding mud on top of a base road material. And of course, decals. Decals are really fun to make as well. When I was working on games at Blizzard, like making the textures and stuff like that and applying them to the world were really fun with the decals also. Uh, Decals, these are like separate projected materials applied on top of existing surfaces. You can use them for like bullet holes, cracks, stains, leaks, stickers, graffiti, labels, and all the details on top elements. So together, layering and decals let you start from simple base materials and then add localized story and variation where it matters without creating a brand new texture for every little detail. So now let's connect materials to performance, right? Starting with textures. This is very important for you all when you're working on your games. Optimization, performance. You want to make sure your game is playable, and this highly affects that as well. Every texture costs VRAM and bandwidth. A 4K texture is 4 times the pixel of a 2K texture, which is 4 times a 1K, of course. That adds up very quickly. So teams often define uh, texture budgets as well. Only key hero assets get very high resolution. Regular props use mid-range like 1K. Small objects use smaller maps. And to save memory, which is very important, it's common to pack multiple grayscale maps into a single RGB texture. For example, the R for is AO, G is roughness, and B is equal to metallic as well. So the main idea is that don't treat textures as free. Every material decision is also a memory decision as well. So the second performance dimension is shader complexity and transparency. Each material is a shader, a program running on the GPU like we talked about. More texture samples, more branches, and more heavy math all cost time. It's fine for a few special materials, but if every surface has a very complex shader, performance will suffer. And transparency is particularly tricky. Transparent surfaces are usually rendered after opaque ones and often require sorting. When multiple transparent surfaces overlap, the GPU shades the same pixel multiple times. This is called overdraw, and I'm guessing you guys have heard of that as well. Practical takeaways for this are like you want to keep most materials relatively simple and opaque. Use complex or transparent materials only where they really matter, and minimize layers of overlapping transparency. All right. So a practical way to keep control is to think in terms of a material library, right? So when you work on a project, a good library has a relatively small number of base materials, smartly designed, well tested. So really think about it for your projects when you're working on this kind of stuff. Many instances of those bases are providing color and roughness variations, reuse across assets and levels instead of new materials for everything. And this gives you more predictable performance because you know what each base material costs. A more consistent look because similar surfaces share the same underlying shader. And simpler maintenance because fixing or improving one base material benefits all instances. And this is a big part of how large teams keep their projects manageable. So this is really important. So for those of you who are struggling with performance right now in your game, think about this. Go back to how you have things set up. See where you can like optimize things within your material and shader library setup as well. So think about it all the time during the development process. Okay, so guess we're doing good. Okay, on time. Even without touching an engine, right? You can practice reading materials by looking at games you already play. I do this all the time. When I'm playing a game, like recently, I don't know who was playing Arc Raiders. That's a very well optimized game, by the way. Runs are great. It looks really great as well. You go in and take a look at the shaders, how people you zoom in, and are like, wow, that looks really great. And you get inspired and you try to recreate it. Like when you pause and look at a scene, ask yourself a couple of questions. One, what type of material is this? Is that a surface wood, metal, glass, fabric, plastic, stone, etc.? What are its PBR properties? Does it look like metallic or non-metal? Is it glossy or matte? What does that say about roughness? Where might a normal map be adding detail? How is it likely textured? Is this surface probably using a tiling material? Does it look like a unique baked texture or for a hero asset? And also, could multiple objects be sharing a trim style sheet? So you can think about those kind of things. And where do you see layering or decals? Are there stains, cracks, bullet impacts, stickers, labels that look like they're added on top? So when you are playing and you can thinking this way turns every game into a case study. So you learn also when you're playing the game. You're training your eye to see behind the final image and understand the material decisions that a game you're playing made when they shipped it. So let's pull together so far what we learned, the key points, and especially the why behind them now. Okay? So materials are very important, are essential to the believability and mood of your game. Players might not know the terminology, but they instantly feel that when surfaces are wrong. So, very important. PBR gives you predictable behavior. Material set up properly will behave sensibly under different lights, which saves you time and rework as well. Every material decision is also a performance decision. Just don't randomly put things together. It doesn't help anybody. Texture size, number of textures, shader complexity, and transparency all affect memory and frame rate. Understanding materials helps you communicate better with artists, tech artists, and programmers because you can talk in precise terms instead of just saying it looks weird. You want to be able to exactly explain why does it look weird. Be descriptive when you see problems within your games, right? So mastering materials isn't just about making things prettier, right? It's about making visuals that are believable, efficient, and maintainable in a real production environment. And as we're wrapping up now, to close, here are some actionable ways to practice. And I was talking about this, earlier when we started the talk, is that even without following along in an engine right now, you want to start describing real-world objects in PBR terms. When you pick up your phone, ask metallic or not, think about those kind of things because it helps you understand how to build something like that for a game. Roughness, does it have a fine surface, detail you'd put in a normal map? And this is all the kind of stuff that we did in art school. And in school when I was going, making my own games and movies when building these kind of things. When you play games, pause and analyze the materials, like we talked about earlier. What types are you seeing? What are their roughnesses and metallic properties? Where might they be using tiling? Where are the decals adding detail? So when you do get back into your engine, try building a small material library rather than random one-off materials. A few solid bases and multiple instances. And as you experiment also, always keep performance in mind. Ask, how many textures am I using? How complex is the shader? Do I really need the transparency there? So when you're making anything in game, think about performance and optimization from the get-go, even with materials and shaders. So the more you practice seeing materials this way, the more natural it becomes to designing them well. So I guess, yeah, we're going to be wrapping up now, and we've finished a little bit early. So if we do have time for questions, Joan. So thanks for listening, and now I'm happy to take any questions you guys want to ask.